Welcome to video lecture G1. This one is on inner products and distance in Rn. I'll be your protagonist, Tom Roby, and here are the outline and objectives. We'll define the inner product of two vectors, u and v, in R to the n, and analyze its essential properties, sometimes called the dot product. We'll define the length of a vector in terms of the dot product, and then we'll generalize the notion of perpendicularity from 2 and 3 dimensions to define two vectors to be orthogonal, which will be when their dot product is 0. So this is the lecture where we start to introduce geometry, which we haven't done explicitly. And the way we're doing it, we'll be talking about R to the n, but the axioms that we'll give, the basic propositions, will allow us to, later on in your math career, you'll look at generalized inner products that will serve the same function of talking about basically adding a geometrical component. This way we can talk about the angle between two vectors, for example. Okay, so here's the first idea, which is that sometimes we know that ax equals b doesn't always have a solution, right? And we know how to check when ax equals b does have a solution. But when it doesn't have a solution, you might still want a solution. Your boss might say, you know, I don't care if it's impossible, I still need a solution, right? You want to hit some output target, and you want to control the inputs x so that you get the output target. There's no x that'll do it. What's the best approximation? What can you do when you have an overly constrained system? This kind of thing comes up all the time in applications. And let's just look at a kind of bare bones, very simplistic example to convey the idea of this. Suppose that you had something like this, a matrix 6, 2, 3, 1, and you want to get to 4, 3, right? So now if you notice 6, 2, and 3, 1 are scalar multiples of each other. So if I look at the image, the range of that linear transformation, in other words, the column space, then in R2, the column space of this matrix is just going to be all multiples of things that are like 3, 1, right? So there's this vector 3, 1, and 6, 2 is a multiple of it. And so the only thing I can get, so this is the column space of A, is just that line. And now the boss says I need to get to 4, 3, so that's some point over here, right? How can I get to 4, 3? Well, I can't get to 4, 3. But the best approximation to this is going to be the point on this line that's closest to this point that I want to get to. So instead of, you know, there's a whole bunch of places I could go to, but really this point here is the best approximation, right? It's the best approximate output that I can hope to get if I'm trying to get to 4, 3. Okay? So, but in order to talk about that, I need to say, well, what do I mean by the best? Well, I mean that the distance from this point to the line is the shortest. In order to talk about distance, I really need to talk about geometry. So this is the first place where we're explicitly, in the things that we're doing in linear algebra, adding the geometrical component in. Now here's the definition. Computationally, this is quite easy to manage. The inner product or dot product of two vectors u and v is just given by, you take the row vector u and you multiply it by the column vector v. You can just think of that as matrix multiplication. But what it boils down to is taking this convolution, if you like, where you take u1 times v1 plus u2 times v2 dot 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 plus un times vn. Okay, so that is the dot product, and you know we can just compute a simple example to make sure we're all on the same page. If I want to take the dot product of, say, 2, negative 1, 3 with 1, 0, minus 2, what would I get? So, well, I take 2 times 1, 2 times 1, plus minus 1 times 0, plus 3 times minus 2, and this is 0, this is minus 6, plus 2 is negative 4. So there it is. There's the dot product of those two vectors. And notice that my input is 2 vectors and my output is a single number, a scalar. Okay? So that's why sometimes it's also called a scalar product, because it inputs vectors and outputs scalars. This works in any n dimensions. There's no, you notice that we don't have any real notion of multiplying two vectors and getting as an output another vector. Right? It works in R3 with the cross product, but that's really a special case, and there's no general way in R to the n to find a multiplication operator that makes good sense, that has the properties we would want multiplication to have in n-dimensional space in general. But here are the properties that an inner product, a scalar product, can and should satisfy. So notice that if I had switched the order of these things, so if I decided to instead multiply 1, 0, negative 2 times 2 minus 1, 3, what would have happened? Well, then I would have had 1 times 2 plus 0 times minus 1 plus minus 2 times 3, and that would have still been minus 4, right? Because it doesn't matter which order, it's commutative on each of the individual numbers, and then the addition is happening the same way. So it's clear that this inner product satisfies u dot v equals v dot u, and sometimes that's when you're talking about it. Sometimes people use different notation for these things. Sometimes people will write, instead of u dot v, people will write u comma v or angle brackets or something. They'll write that for u dot v, but it's still, input is two vectors and the output is a scalar. In this case, you'll talk about this inner product as being symmetric. So commutative or symmetric is the property that we're dealing with here. And now for this one, well, it looks like the distributive property, right? And that's really what it is. And this is saying that scalars pass through this inner product in the natural way. These properties together, especially if you think about it in this way, get to be called bilinearity. So this property here is called commutative, or sometimes symmetric. And then these two here are sometimes called bilinearity. So if you see these terms later on, somebody says we have a symmetric bilinear form, they're not talking about anything that you should think is amazing or a big deal. It's just the natural properties you want this kind of product to have. And so finally, this last one is sometimes called positive definite. So I guess I'll write that down here. Definite. Okay, so the positive part is saying really means non-negative. So if I take the inner product of two vectors, I always get something bigger than or equal to 0. And the definiteness is saying, well, if I multiply, if the dot product of a vector with another vector is 0, then that can happen if and only if the vector is 0. And from this definition, that's pretty obvious, right? Because if u and v are the same, then this becomes u1 squared plus u2 squared plus dot dot plus un squared. So if I'm summing the squares of something, that has to be non-negative, and it can only be 0 if each of these terms is 0. Okay, so that proves this last one. And finally, for like 2 and 3, you can do the proof by just noticing, right? One way of thinking about this formula here is that uv is really equal to the vector u transpose times the vector v. Okay, just matrix multiplication, right? Because u starts off as being a column vector. I transpose it to make it a row vector if I want to do that kind of, if I want to think about it as matrix multiplication. And then, like properties 2 and 3, the bilinearity will follow easily along the following line. So let me just show you 2. So proof of 2. So if I'm looking at u plus v dot w is equal to u plus v transpose times w, just matrix multiplication, right? So I've replaced the dot product with this transpose thing, but now I know that the transpose of a sum is just the sum of the transposes, right? That's true for any matrix. It's certainly true here. So then this is equal to u, the vector u transpose plus the vector v transpose, still have parentheses, times w, the vector w. Now we know that that matrix multiplication has this, or matrix vector multiplication, however you want to think about it, has this property of distributivity. So then this is just U transpose V, U transpose W plus V transpose W, and then each of these is just equal to U dot W plus V dot W. Okay, so there's not much to this proposition. The key thing about isolating these properties, though, is that these are the properties that you want a general bilinear form to have. And so people will define bilinear forms in other ways. For example, if you have functions, say periodic functions, if you're doing Fourier analysis, then you want to think about two functions from 0 to 2 pi, say, or from minus pi to pi. And so there your orthogonality relation is, you'll say that people will write something like inner product fg is equal to the integral from, say, minus pi to pi of f of t times g of t dt. And it turns out that this also satisfies these properties. So it makes a very good inner product, and it's the inner product with respect to which you can think about Fourier analysis as representing things with respect to a very nice basis of sines and functions and sines and cosines. And another example for those of you who end up taking probability, Math 3160 at UConn, is covariance of two random variables. I guess I'll call them x and y. The covariance of two random variables is also an inner product. And so all those properties that get stated about it are really just these properties, you know, sometimes in disguise if your instructor doesn't tell you that really this is just an inner product. Okay. Okay, so now that we've talked about the inner product, we can define the length of vectors in Rn in terms of that inner product. So here's the definition. Again, it's computationally simple. All you want to do to find the length is take the dot product of something with itself and then take its square root. And again, this kind of definition generalizes even if you've defined your inner product axiomatically. And so this is equal to the square root of the sum of the squares. It's the length or norm of the vector. And we'll define a unit vector to be one that has unit length. And there are many times in which we want to think about unit vectors because, for example, you could think about, if you want to talk about a direction, you can describe it by a unit vector. You might have seen this in vector calculus, right? You can, you know, the vector that we just saw, 3, 1 points in the same direction as 6, 2 points in the same direction as 9, 3. But I could just think about them all as pointing in the right. I could just say, what's the unit vector? And that gives me a well-defined way to talk about that. So let's look at an example. So suppose I want to take the norm of the vector minus 2, 4, 1, 2. This is really a vector in R4, and I would ordinarily write a vector in R4. So I think I'm calling this vector x over here. So I would call this vector, I would normally write it as negative 2, 4, 1, 2. But it gets hard to write things. There's not a lot of vertical space, especially the way I'm trying to minimize the number of slides I'm using. And even in the textbook, sometimes this comes up. So just to make your writing take up less space, sometimes we'll write vectors in this horizontal notation, right? And notice that we use the round parentheses instead of square brackets to be clear about that. Whereas on the earlier slide, when I meant for my vector to be a row vector back here, I wrote it as a row vector, right? But here with commas and round brackets, I mean this is just a pseudonym for this vertical vector. Okay, but so whatever, in any case, if I take the norm of it, I'm taking the dot product of it with itself, which of course has to be positive, right? So that we can take the square root. And so if you compute this out, that you'll see that you get the square root of 25, which is 5. Now if I want a unit vector, the most convenient thing, sometimes I want a unit vector pointing in the direction of a given vector. And the easiest way to do that is to just take a vector and divide by its norm. Okay? And if I do that, then I'll get a vector which has to be a unit vector. So why is that? Well, if you take a vector and divide it by its norm, and then you say, is it a unit vector or not? Well, what are you doing? Remember, the norm is now a scalar, right? This is just some number. So if I take the norm of x divided by the norm of x. Well, a property, because we could pull, I guess I need to show you one thing, right, which is that I claim, so first let me do this computation. I claim that I can pull any factor, whatever it is. If I think of this as a factor c, I can pull that out of the norm. So this is 1 over the norm of x times the norm of x, and that's just equal to 1. But the lemma that I'm using here is that what happens when I take the norm of some scalar times a vector, right? So if I take the norm of c times a vector, well, by definition, well, if I look at the square of that, often we do these computations, we don't want to keep writing the square root. So we'll just say, what happens when I take the square of that? Well, the square of that is just the dot product, the inner product of CV with CV. So there's a dot in there. Okay, so now if I take the dot product of CV with CV, remember that these factors can all pull out. So I can pull one c out and another c out, and I end up with c squared times v dot v, and that's just c squared times the norm of v squared. Okay, so the norm of cv, the square of this, is equal to c squared norm of v squared. And so if I take the square root of each of these things, that implies that the norm of, so if I rescale a vector, then I just rescale its length. And that should seem obvious enough, right? If I make a vector, if I multiply a vector by 2, I get a new vector, and that vector has twice the length of the previous vector. So that's not very exciting, but the point is that I can prove it formally from those properties. Okay, so now, here's the thing. Once you know what length is, you also know what distance is, because the distance between two things is just the length of their difference. And this, should go back even to elementary school on the real line, right? If I want to know what the distance is between 1, 2, 3, 4 and -3, well, that distance is going to be, and it doesn't matter, distance is symmetric, right? So like same thing as the distance between -3 and 4. Well, this distance should be the absolute value of -3 minus 4, which is the absolute value of -7, which is 7. Okay? So absolute value is basically the norm. It actually is equivalent to this, right? If you only have one variable, then you're just taking the square root of x1 squared. Square root of x squared is the absolute value. So this is the R1 version of this, is the absolute value. Now, if you want to think about an R2 version of this, let's see, what am I going to do then? So now in R2, I will maybe I need to go a little further out. Okay, so in R2, what happens? Suppose I've got a vector. So I'll call this vector u. And I've got another vector, which I'll call v going out this way. And what is u minus v? Well, there's two different ways to think about it. You can just think that u minus v should be the vector that does this. So if it's u minus v, then it should be going this way, right? So u minus v is that vector. If you're not so sure about this, you certainly know how to add vectors, so you can always add u. U minus v is the same as u plus negative v, right? So if I think about negative v out here, then if I add that to u, then I get something like that maybe. Okay, so this this should be u minus v. So u minus v is u minus v is really this vector, which is the same as this vector. It's the same length and perpendicular. So this distance has the length u minus v. So it's the length of the side of this triangle when I look at the vectors defined by u and v. Okay, and so that's the distance. So now I want to define orthogonality. But the way I want to do that is to do a computation for you. So here's the computation. So I need another picture. And here's what the other picture looks like. Suppose I've got some vector u. So I'll draw a similar picture again. So I've got some vector u. So u is sitting out here. And now, what do I mean if I want it to be perpendicular? Well, if it's perpendicular, it sort of looks like that, right? So here's v. And now here's minus v. And so I can imagine that I've got this whole line here. And now for u and v to be perpendicular, what that really means is that this distance and this distance have to be the same. Okay? So try to convince yourself geometrically that that makes sense, that if this line, instead of being perpendicular, were rotated some, then this distance would be shorter and that distance would be longer. Okay? So what I want to do is define orthogonality, or see how orthogonality ties up well with this particular concept. So if I do this, then this is the vector u minus v, and this has length u minus v, and this has length u minus v. Okay? Now if I want those to be the same, what happens? So here's my computation. So if I compute the norm of u minus v squared, well, that just means u minus v dot u minus v. And now I can use the fact that this is distributive property, tells me that I just get 4 terms here. So I'll end up with u dot u plus v dot v, and then I'll have a minus v dot u and a minus u dot v. Okay, so I'll end up with u dot u minus u dot v plus v dot u, or no, minus v dot u plus v dot v. So let me clarify that. That's just a minus. Okay, and so what's that? Well, that means I get the norm of u squared, and then plus the norm of v squared. So I'll bring these two over. And then I've got minus 2 u times u dot v. Okay, so the inner product of u dot v plays a role in this computation of this length. Now, if I do the same computation for u plus v, u minus v, I'll get everything will be the same, except I'll get plus signs here. So this will be equal to the norm of u squared plus the norm of v squared plus 2 u dot v. Now my claim is that for things to be perpendicular, these guys have to be equal. So if these guys are equal to each other, what does that mean? So in order for these to be equal, that means that these guys have to be equal. And if these guys are equal, well, those cancel, and I'm just left with 4 u dot v equals 0. So that can happen if and only if 4 times u dot v equals 0, which is if and only if u dot v equals 0. Okay. So that's the key computation. It's not hard. It follows exactly from all these properties that are straightforward for us to see and probably seem pretty natural to you. And in fact, maybe you've seen dot products a little bit before in, say, vector calculus. But so here we are. It makes sense now to say that two vectors u and v and r to the n, so we generalize to n-dimensional space, are orthogonal if their inner product is 0, their dot product is 0. Okay? And so this is the computation in the picture that illustrates that. And so, in fact, what I've really done is I've proven a kind of version of the Pythagorean theorem here. Right? Two vectors, u and v and r to the n, are orthogonal if and only if this is true. Right? Because, well, we just computed u plus v squared is u squared plus norm of u squared plus norm of v squared plus 2 u dot v. So in order for this equality to hold, this part must be 0. 2u dot v must be 0, so therefore u dot v must be 0. So that just follows from the definition. Okay, so all these pieces should tie together, and if you think about distance of u minus v, I guess there's one other way in which the distance of u minus v should make sense to you, which is that if you think about u minus v as being u1, as being in terms of a vector, it would be u1 minus v1, u2 minus v2, and so on in coordinates. That's just what you're plugging in here. So you get the square root of u1 minus v1 squared plus u2 minus v2 squared plus and so on. So that's the usual distance formula that you know about. And there's one last connection to make. If you've ever seen, you might have seen the dot product before, for example, in multivariable calculus, done in the following way. So let's see, I can write down here. So you might have seen a formula that looks like this. U dot v equals the norm of u times the norm of v, the length of u times the length of v, times the cosine of theta, where theta is the angle in between them. Okay, so let's see if that definition makes sense here. So in the case for orthogonality, right, you would want u dot v to be 0. So in the case where they're orthogonal, well, then the angle between them is 90 degrees, right? So in that case, you'd be having theta would be 90 degrees. And if theta is 90 degrees, then the cosine of 90 degrees is 0. Okay, so that does tie up with what we know before. And in fact, this property is equivalent to what's sometimes called the law of cosines, if you ever saw that maybe in high school. But the main point of this is that this also, if you wanted to define a notion of an angle in r to the n, now you have a way of doing it. Namely, you can just define the cosine of the angle between them to be, using this formula, we know what u dot v is. And now we're dividing by the norm of u times the norm of v. All right, that's the cosine of theta, and so then you can just define theta to be the arc cosine of that. So once you know what the cosine of theta is, you know what theta is. Okay, and so that's it for video lecture G1. Thank you very much for your kind attention.